Here is a fantastic problem from the USA Mathematical Olympiad competition. We need to find all positive integers k that make this expression an integer for every single positive integer n. This blend of binomial coefficients and number theory looks intimidating, but we're going to dismantle it step by step. Let's call our expression e of n and k. The condition is that this must be an integer for all positive n. A great starting point in any for-all-n problem is to test the simplest case. Let's see what happens when k is equal to 1. Here's our expression again. Let's substitute k equals 1. The expression simplifies slightly. This sum is a classic identity. From the binomial theorem, we know this is equivalent to the expansion of 1 plus 1 to the power of n. This substitution makes the sum much simpler to evaluate. So for k equals 1, our condition is that 2 to the n divided by n plus 1 must be an integer for all n. Is this true? Let's check a simple case, say n equals 2. Plugging in n equals 2, we get 4/3. This is not an integer, therefore k equals 1 is not a solution. That test was very revealing. Let's use the same value, n equals 2, but for a general k this time, to see if we can find a general rule that k must obey. We set n equals 2 in the original expression. Let's expand this sum. The binomial coefficients for en equals 2 are 1, 2, and 1. The sum has 3 terms. Substituting the values gives 1 to the k plus 2 to the k plus 1 to the k. This simplifies to 2 plus 2 to the k, all divided by 3. For this to be an integer, the numerator must be divisible by 3. In terms of modular arithmetic, 2 plus 2 to the k must be congruent to 0 modulo 3. To find the condition on k, we need to isolate the term 2 to the k. Let's move the 2 to the other side. Subtracting 2 from both sides gives -2, which is congruent to 1 modulo 3. Let's examine the powers of 2 modulo 3. The powers of 2 alternate between 2 and 1. The congruence holds only when the exponent is even. This gives us a powerful necessary condition. K must be a positive even integer. Now we have a hypothesis. The solutions are the even integers. Let's prove that odd integers can't be solutions. We will show that for any odd k, we can find an n that makes the expression fail. Let's assume k is odd. Our expression now has a prime in the denominator, which is very useful for modular arithmetic. For this to be an integer, the sum in the numerator must be divisible by p. A consequence of Lucas's theorem gives us a beautiful congruence. P minus 1 choose I as congruent to -1 to the I, modulo p. This is true because, modulo p, each term p minus y in the numerator is simply congruent to -I, applying this to each term in our sum. The entire sum becomes congruent to the sum of -1 to the I, all raised to the power k. And now we use our assumption. K is odd. Since k is odd, -1 to the I to the k is just -1 to the I. What is this sum? It's an alternating series, 1 minus 1 plus 1 minus 1. Since p is an odd prime, p minus 1 is even. The series has p terms and ends with a plus 1. The sum pairs up to 0, leaving a final term of 1. The sum is congruent to 1 modulo p. This means the numerator is not divisible by p. And if the numerator is not divisible by the prime p in the denominator, the expression cannot be an integer. This completes the proof. So k cannot be an odd integer. We've proven k must be even. Now we must prove that all positive even integers are indeed solutions. Let's start with the first case to build intuition. Let's examine the case where k equals 2. This sum has a famous closed form known as Dixon's identity. The sum of the squares of the binomial coefficients is equal to 2. And chosen. This expression is precisely the formula for the n-manist Catalan number, which is famously always an integer. So k equals 2 is a solution. Now for the general proof. Let k be any positive even integer, say k equals 2m. We must show that n plus 1 divides the sum for all n. To do this, we'll show that for any prime power p to the alpha that exactly divides n plus 1, p to the alpha also divides the sum s. Let's first prove it for a single prime p dividing n plus 1. We can write n as pq minus 1 for some integer q. By Lucas's theorem, we can analyze the binomial coefficient by looking at the base minus p representations of n and I. Since n has trailing digits of p minus 1 in base p, the leading term of the congruence is p minus 1, choose I0, which is negative 1 to the I0. Here is the crucial step. Because our exponent k equals 2m is even, the negative 1 term vanishes. The congruence becomes independent of the least significant digit, I0. We can now group the terms by the value of I0. For each fixed set of higher digits, we sum over all p possible values of I0, from 0 to p minus 1. This introduces a factor of p into the sum. Therefore, the entire sum s is congruent to 0 modulo p. While the full proof is more technical, this logic can be extended to show divisibility by any prime power p to the alpha dividing n plus 1. This confirms that n plus 1 divides ss. We have shown that k must be even, and that if k is even, the condition holds. Therefore, the set of solutions is all positive even integers. So let's put it all together. We were looking for all positive integers k that make this expression an integer for all positive n. We found that k must be even by testing n equals 2. We then proved that any odd k fails by choosing n to be p minus 1. Finally, we proved rigorously that all even integers are solutions using Lucas's theorem and the properties of binomial coefficients. The final answer is that k must be a positive even integer. Thanks for watching. Please like and subscribe for more math content.